but there's a harmonic right there. So that's 1, 2, 3, 4, 5, 6. It's the 7th harmonic. I apply more tension so that the wave travels faster.
Well,
4th harmonic. I'm hoping that you can see it.
yeah.
Yeah.
Pull even more. At some point that's going to start moving.
Is it turning like?
There we go. That's the 3rd harmonic. What's your question?
Is it turning on? Is it staying on the whole time?
Yes.
Yeah.
Is that 3, 4? That's 4th harmonic.
Do you want somebody to hold that end down so that you can move?
That probably would be convenient.
So
Which
would
end did
this-
you want that in?
Yeah, sure.
Would this also equate to like those, have you ever been to a wave pool where they create waves and then they push?
I'm assuming it's the same type principle that
Yeah.
you'll have
Can I
waves
hold the rod?
overlapping. Pardon?
Can I hold the rod?
Oh, yeah, yeah. All right, 3rd harmonic right there. Recognize how much tension I'm applying to this thing. 2nd harmonic. Yeah, it looks like I'm not getting better than that. All right, thank you. This was a lab, when we went into lockdown, this was one of the labs that was gonna happen that semester. And I wanted a longer string so that we could more easily pick up the higher harmonics. And so I had so much weight hanging off, I think it was like 4 kilograms held on this tiny bit of string, that it ended up breaking. So starting over, I had to edit out more profanity on that video than any other video I've done.
It happens.
Yeah. And then the worst of it was that here you could see I think you could clearly see the harmonics.
Yeah.
But the refresh rate on the camera matched about that of the string. And so you basically saw the string from an overhead point of view, the string would look like that and would sort of stay like that.
Oh.
You actually could not see it vibrating back and forth.
Oh, because the
It would just-
camera shutter
Refresh
not
rate.
taking enough photos per second.
If you've ever seen the anti-grav helicopter, it's very similar to that. Now, the way that I was able to demonstrate that it was actually doing anything is I put my fingernail next to it. Guess not really. You can hear that extra vibration as it hits against my finger. Now, in this one, you can see it, but I keep wanting to redo it, but also don't want to deal with the frustration.
You know, it sounds, I don't know if this sounds like a good idea or not, but it might be something that would be really cool if you could set up like a giant version of that and have it like, I don't know, maybe like a table or 2 length long, and then it would create larger waves, that way you could see it a little larger. But I don't know what the cost of that would be and how much time you'd have to put into it.
Yeah, and ideally, in the ideal situation, it's an ideal string, it has no mass.
Yeah,
So if you start getting longer and longer piece of string, then suddenly that mass, it becomes questionable whether you can actually ignore it or not.
right.
So that's the other, how much reality do you want to bring into it?
Right.
Dr. Faust, when you added more tension to the string, did the nodes increase or decrease?
Decreased,
Yeah.
because the waves are traveling faster, and so you're gonna get, well, we have the speed of the wave is equal to the frequency times the wavelength, also equal to the tension times, divided by the linear density. This is what we're working with here. So frequency squared times the wavelength squared is equal to the tension divided by the linear density. And the frequency is pretty much set, that's based upon what the vibrator is doing. And so the wavelength, tension over mu frequency, So there's a relationship between the tension in the string and the wavelength. So as the tension increases, we're increasing the wavelength, which means that we're gonna see a longer distance between each node.
Okay, gotcha.
Question. You might what you just explained might answer this, but when we were outside and you did the first harmonic with the slinky, it seemed like there was less tension there, or am I incorrect?
Out there, I was changing the harmonic based by changing the frequency.
Okay,
Here, the frequency is set,
okay, gotcha.
and that's the big difference between those two situations.
Okay,
Does that address?
yeah, that makes
Okay.
sense, yeah.
All right, so let's take a look at the harmonic specifically with two fixed ends, which is what we had there. We had the end that's tied there that's considered to be a fixed end, and then where I was holding it. So the simplest, that's the simplest harmonic. That's for two fixed ends. This is the first harmonic. So the question is, how many waves is that? Well, if you think about a wave, you think about a sine wave or a cosine wave, that's basically a wave right there. So this is considered to be one wave. So how many waves is this?
1/2?
All right, so if the distance from end to end is some length L, then L is equal to a half of a wavelength. Or the wavelength is equal to twice whatever L is. The second harmonic, how many waves? One. Yep. Third harmonic,
3 halves?
or, yeah, 3/2.
1.5?
Or the wavelength is equal to 2/3 of the length.
Oh,
That's the wavelength right there, it's 2/3 of that length right there.
okay.
And so on. Notice that each time I increase the harmonic, I increase it a half a wave. The restriction is with a fixed end, the fixed end is a node, and so I have a node at the end every single time. Suppose I have one fixed, one free end. One fixed, one free. Well, a fixed end is a node and a free end is an antinode, so the simplest one looks like that. How many waves is that?
A quarter of a wave?
Yes. So L, so again, if this distance here is L, that's a quarter of a wavelength. Or the wavelength is equal to 4 times L, whichever way you want to look at it. The next simplest one. How many waves is that?
1 1/4?
3/4?
3/4, yeah.
Every time we go to the next one, we add a half a wave. Now this is where I consider the language to be confusing. This is the first harmonic. This is the third harmonic. With the one fixed, one free, you add a half wave every single time, but you're only doing odd harmonics.
Would you be able to maybe match that up with the numerator and the
Yes. Yeah.
okay.
And ultimately, that's where it's coming from.
Okay, gotcha.
So here it's 1/2, 2/2, 3/2,
Right.
first, second, third harmonic. Now, in this particular situation, physically what we're talking about here is we can represent it with this. We can send the sound wave down. It's not supposed to spin. this tuning fork is 320 hertz, which means that if I hit it, it's going to vibrate back and forth 320 times a second. Looking for the striker. Oh, there it is. If you're ever dealing with the experiments with tuning forks, please don't bang metal on metal. It gets a really loud sound, but it also starts to do damage. You can see these have various nicks in them. But I'm hoping you can all hear that. What's happening is this thing's vibrating back and forth like this, pushing air in one direction, compressing, bopping in the other direction, creating rarefied space, then compression, rarefaction. Sound waves are going down to the bottom of the tube and coming back out. We have water in here. I can adjust the height of the water just by moving this. As I lift this up, water will come up. As I go down, water will drop down. The height of the water in the tube should match the height of the water in here. So we can predict where we would get the first harmonic. So that was 320 hertz. Yeah. So the frequency, 320 hertz. We're dealing with sound. Speed of sound is not a constant, but it's relatively stable here in this room right now. It's going to be approximately 343 meters a second-ish. We're within 2 meters per second. So I can figure out what the wavelength of the sound wave is, because I know that the speed is frequency times the wavelength. So the wavelength is speed divided by the frequency. So that's 343 meters per second divided by 320 hertz.
Is frequency always going to be in hertz?
That's the standard unit for it.
1.071.875.
Instead of 8?
No, keep going. Yeah, that's it.
This is my international, whatever units look.
Cycles per second, or hertz.
So,
Wavelength, oh.
So units? Meters.
Meters.
Now the first harmonic should happen at a quarter of that. So the length of my air tube, because basically I have a fixed end here, I have a free end here, fixed end where the water is. The first harmonic should happen at a quarter of this number right here.
0.2679
Meters.
meters.
So I would expect it when the air column here is 26, little under 27 centimeters, we should reach a harmonic. Right now, sound wave is going down, bouncing back, there's some interference, we're not getting that maximum amount of constructive interference. So what would you expect to hear though when we get this? So imagine this sideways.
What would we hear?
Yeah, how do we know if we actually hit the harmonic or not?
Would we get quiet? Wouldn't it get much louder because it's constructive?
Much louder. This is at the open end right here. This is the point where we get into the biggest swings back and forth, which is, from an eardrum point of view, push in and pull out of your eardrum the most. So let's see how close we can get. Now, there are 2 centimeters gap, there's a 2 centimeter gap between the top and where 0 is here. Not sure still 100% why that is the case, but it was consistent among all the ones we got. So when I would expect it to be somewhere around here, that's where the harmonic should occur, somewhere around there. we go, this is the first harmonic. And that's at about 23 centimeters plus the extra 2. So we're getting to about 25 centimeters. We predicted, so we're 2 centimeters off. It's physics.
Yeah.
Now, the third harmonic should occur at 3 times whatever the first harmonic was. It's a lot quieter, so I'm not gonna do that one, but it's down there somewhere. The lab works reasonably well as long as you don't hit the false harmonics. There's sometimes if we started at the top and worked our way down, it was loudest at the first harmonic. It gets a little bit louder somewhere in between there, and then it quiets off, gets quieter, and then it's louder at the first harmonic. But some people mistake that the first time where it's a little bit louder as the first harmonic, and so now the numbering is completely off, and so you can get some really bad results if you mess that part up. So let's take a look at 2 free ends. Free end is an antinode, so 2 free. And that's the simplest of the harmonics. How many waves is that?
One.
Half of one? It's half of one. Basically, if that's a full wave, we basically chop the quarters off at the end. The next one, without even drawing it, how many wavelengths is the next one gonna be?
One.
And the next one?
2.
2.
3 halves.
Either one. 3 halves or 1.5. That should be more symmetric, but I'm trusting your notes will nail it. So second harmonic, third harmonic, L is equal to lambda, L is equal to 3 halves of lambda, or lambda is equal to 2/3. Now 2 free ends would be like if we had a tube here with both ends open and we swung it around, and you can hear the harmonics. That's actually the second harmonic, third, fourth, fifth. Now what's happening from a physics point of view is this thing swings around. This tip over here is obviously traveling faster than this end down here. As this end travels faster, there's a drop in air pressure right there. And with a drop in air pressure here, air is getting sucked up through the tube. For the first harmonic, I can't swing it fast enough to get enough air going through it in order for the ridges get the air molecules start vibrating. But I have to swing it fast enough for enough air to get sucked through, which happens at the second harmonic. But let's predict. We're hearing sound, so the speed is around 343 meters per second. The first harmonic happens when the wavelength is twice L, so we need to know what is the length here.
Just at least 2.
At least 2.
Yeah.
Any particular units? 2 whatevers.
Yeah. That's what my friends always say whenever I ask them, what is this? And they're like, well, it's at least 4. I'm like, thank you.
A unit system does exist where that is true. All right, so I'm basically going to do it from this ridge to the end here. I have another tube which I've used quite a bit and probably in all the videos before this year. It's a red one that's a lot more beat up than this is, but they don't have this part right here, which is basically the handhold. So I'm going to start there. I'm going to stretch it just a little bit because as I swing it, it will naturally stretch out. So I don't want to do it too much, but get that at the end. And so It's looking like about 79 centimeters is the length. 0.79 meters. So for the first harmonic, the wavelength happens at twice that, so 1.58 meters, if I did my math right. So the frequency of the first harmonic, well, that's the speed divided by the wavelength. 343 divided by 1.58. Do something.
$217.0886.
Wait, say it again?
217.0886.
Units?
Hertz.
This is,
All right, so 217 hertz. 217.1. That's the first harmonic right there. There. We nailed that.
Sounds good.
So let's take a look at the second harmonic. Second harmonic, it's a full wave inside that tube, so L is equal to the wavelength. So my frequency,
is 0.7, wait,
343 divided by 0.79.
$434.2.
Should just be twice what we just got right there. So 434.2. Now,